Hi, welcome to the third lesson of this first section in Logic, Language and Information 2. We've seen how propositions have got an internal structure involving names and predicates, and how we need to use this structure to explain the validity of some obviously valid arguments. The next thing we need to examine is the quantifier, that part of our language that enables us to not only talk about specific and particular things, but to generalize. We've already seen atomic sentences analyzed like this, using names and predicates. Will is a quadruped involves a one-place predicate and a single name. Clancy loves Madison involves a two-place predicate and two names. How are we to analyze the structure of statements like something is a quadruped or Clancy loves someone? These look exactly the same sort of form as Will is a quadruped or Clancy loves Madison. The something or someone can play the same sort of role in a sentence as is played by a name. But can it? Suppose we were to treat something is a quadruped as having the form QS, where the S is kind of like a name. Now, it's not really a name, because nothing is named something, so I'll underline the S here to remind us that it's not really a name. Now, perhaps this will do to display the form of something is a quadruped. Maybe like will is a quadruped, the something is bringing an object to our thought, and then we describe it as being a quadruped, being four-legged. But if you think about it a little more, you'll see that this can't be right. Think of what it might mean to say that something is not a quadruped. If something is a quadruped is QS, then this, I suppose, is not QS. You're taking the S, the something, and saying that it's not Q. But when I say that nothing is a quadruped, I'm denying the claim that something is a quadruped, and I'm taking the claim QS and I'm negating it. And that should be not QS too. But they can't both have that form, because these two statements mean very different things. One says that something's not a quadruped, and the other says that nothing is a quadruped. That's much stronger. Now, what about Clancy loves someone and Madison loves someone? If Clancy loves someone is LCS, then presumably Clancy loves someone and Madison loves someone should be LCS and LMS. But then, how am I to say the different claim that there's someone that Clancy and Madison both love? That there's the same someone? That should also be LCS and LMS. We want a way of understanding the form or structure of these sentences that allows us to see the differences here. We can't just treat someone or something as analogous to names. That's because these statements involve quantifiers. The sum in someone or something plays a really special logical role. We see it in statements like some wombats are hairy-nosed. There are other quantifiers beyond some. The all in all valid arguments with true premises have a true conclusion is also a quantifier. And so is most and many. And so are numerical quantifiers like at least 7 or exactly 23. There are plenty of different quantifiers, each of which select for some number or proportion of objects satisfying a predicate. Some wombats looks for one or a few. All valid arguments select for all of the valid arguments. Most logic students needs a majority from among the logic students, and so on. It's a different mode of picking out objects to describe them from our other technique, that of naming those objects. Now, there's lots to say about the logical behavior of all of these different sorts of quantifiers, but in this subject, when we cover first-order predicate logic, we'll focus on the two quantifiers here which have the most clear and precise behavior, some and all. Now, there have been many different theories about how quantifiers work throughout history, and here in this lesson I'm going to look at just two examples. Now, Aristotle's syllogism provides an understanding of quantifiers. For Aristotle, quantifiers link terms. They link subjects and predicates. Statements like will is a wombat, or all wombats are quadrupeds, or some wombats are hairy-nosed, or no wombats are logic students, have got forms like S is a P, the subject satisfies the predicate, or all S are P, all of these subjects are the predicate, or some S is P, and no S is P. And Aristotle's syllogisms are simple argument forms that relate judgments that have these shapes. Now, this is an interesting and a useful analysis, but it only goes so far. Consider a judgment like, some wombats are hairy-nosed. In this case, some wombats are the subject of the judgment, and we predicate being hairy-nosed of them. Now, if the subject, some wombat, satisfies the predicate, then the statement is said to be true. But consider the conjunction, some wombats are hairy-nosed, and some wombats aren't hairy-nosed. This is true, but what's the subject of the sentence? Some wombats? But which ones? The hairy-nosed ones, which are the subject of the first conjunct, aren't the same subject as the subject of the second conjunct, because that picks out the non-hairy-nosed ones. We use the same phrase to pick them out, though, some wombats. We haven't got much insight into how this works if all we can say is that the subject of the statement is some wombats, and leave it at that. So it was for reasons such as this that the 19th and 20th century saw a revolution in the way that we understand quantifiers. In the work of logicians like Gottlob Frege, we've come to understand quantification in a very different way. In evaluating a quantifier expression, we don't just name a subject to be described. We make or describe a choice. Some wombats are hairy-nosed is true just when there's a choice of wombats that could be made where the wombats chosen are hairy-nosed ones. Now, Frege developed his understanding of quantifiers in his Begriffsschrift, which literally means concept script, a notation for depicting the form or shape of concepts. This is, quite precisely, a very different and, frankly, very inconvenient way to describe the forms of predicate logic. Now, we'll be doing work in this tradition, but with a very different and much simpler notation than the kind of diagrammatic notation that Frege invented. Now, here's how it works. When I say that Will is a wombat and is hairy-nosed, this is the simple conjunction of two predications involving the name Will. But when I say that some wombat is hairy-nosed, then what I'm saying could be satisfied by Will, since he fits the bill, but it doesn't need to be Will to fit that role. It could be anyone. It merely requires something to satisfy the role of being a wombat and being hairy-nosed. So in the formula, we say that Wx and Hx is the role that we're looking to be filled, and we say that what we want is something to fill that role. This backwards Ex indicates that we're after something to fill in that X position. And if there is something that can do that, the statement will be true. This backwards E with the variable X is what we call the existential quantifier. Then, to deny that statement, to say that no wombat is hairy-nosed, it's clear what to do. We just negate the original statement and we say that we can't fill the role for X. It's not the case that there is something that can play that role. Whereas, to say that something isn't a hairy-nosed wombat, you also use the negation, but it now occurs after the quantifier. We're after something that isn't both hairy-nosed and a wombat. And so we're saying we can find something which fills the role of not being a hairy-nosed wombat. Similarly, if I'm to say that Clancy loves something, I say that there is something that fills the LCX role. There's something I can find for X that Clancy loves. So to say that Clancy loves something and that Madison loves something, I can conjoin there is something that Clancy loves with there is something that Madison loves. The first conjunct says that we can fill the X role in LCX, and the second says that we can also fill the X role in LMX. There's no requirement that they be filled with the same thing, just as there's no requirement in the English, in the two uses of the word something, that those two uses pick out the same object. On the other hand, if I want to say that Clancy and Madison love the same thing, I can. I can conjoin LCX and LMX and say that I need the one thing to fill that role. And now it's the one thing that Clancy and Madison both love. Now that's the backward E, the existential quantifier. And that's not the only quantifier we'll look at. So for example, if I say, if Will is a wombat, he's hairy-nosed, then this is a simple conditional. If Will's a wombat, then Will's hairy-nosed. Now, if I want to say that this applies generally, not just to Will, but to all wombats, if I want to say that all wombats are hairy-nosed, I do the same sort of thing. I say that the role wx implies hx applies generally. It applies universally to anything. If x is a wombat, it's hairy-nosed. Now, if I want to say that Will has a friend, this is an existential quantifier statement. There is somebody that fills the role of being a friend to Will. The role fxw, x is a friend of Will, can be filled by something. But if I want to say that that's not just true of Will, but true of every wombat, I can say that the role fy implies there is an x such that fxy is universally satisfied. What that says is that if I choose anything at all, if it's a wombat, then it has some friend. And you'll notice here, because we're talking about two roles, we're talking about the role of being a friend of Will, or being a friend of y in this case. We need a variable x for that. And we've got another variable, the variable y, which is the role that is being filled here of anything that we're checking to see whether, if it's a wombat, if it's got friends. So, on the other hand, if I want to say that Clancy's a friend to all wombats, I say that the role, if you're a wombat, then Clancy's a friend of you, is generally satisfied. If anything's a wombat, Clancy's that thing's friend. But now, if I want to say that it isn't necessarily Clancy that plays that role, but there is something that's a friend of all wombats, I can say that the role for all y, fy implies fxy is played by some object x. So we get, there is something which is playing this role. There is something such that it's a friend of all wombats. Now notice the similarity and the differences between all wombats have friends, which is the one that we have here, and something is a friend to all wombats. You'll notice the content inside, the if wy then fxy, is exactly the same in both cases, but the position of the two quantifiers is different. It occurs in a different order, and the for all y occurs in different places. In the first, we choose the wombats, and for each wombat, we have some choice of a friend. That's why the for all y occurs first, and then under that, we're choosing a friend for each of those wombats that we've chosen. Whereas for the second, we choose the thing that's the friend to all wombats, that's this x thing, and then for each wombat we choose, we need this thing that we've chosen, the x, to be a friend of that wombat. Now, this understanding of quantifiers is extremely powerful. We now have all the tools to define a very expressive vocabulary of logical concepts. So, in the next lesson, I'll put these building blocks together, and we will formally and precisely define the language of first-order predicate logic, and then we can use it to look at the structure of different expressions and then analyze the way that reasoning works in this larger vocabulary.